Okay, well, I think that's probably enough time to do that survey, so let's talk a couple of announcements and then continue the example that we didn't quite finish on Wednesday. The homework 12 is due tonight by 11:59 p.m. And then the only other thing is the final exam, which is due on, well, it's going to happen on Friday the 30th. And so 1 week from now, you'll be a few minutes into that exam. It goes from 12:45 p.m. till 2:45 p.m. Open note, open book. So similar to our last tests where you're not supposed to collaborate with other people, you shouldn't use any websites. What you're turning in is exclusively your work. And then the exam is obtained and submitted through Blackboard. Any questions about the announcements? Okay. By the way, were you able to access that survey using the link? Did that go through? I just set it up this morning, and so I'm hoping that that worked. Thanks, Zach. Thank you, Courtney. Great. All right, so we're continuing with water surface profiles. What are water surface profiles? Remember, gradually varying flow changes very slowly. It's where you have non-uniform flow due to some obstruction or a change in slope or water flowing over the edge of a cliff. There are a variety of things, a change in water, a change in channel width. There are lots of things that can cause non-uniform flow. And what water surface profiles do is try and calculate what is going to be the depth upstream until we get back into the normal depth. So we're going to continue talking about the standard step method. And the standard step method is the one where you can have a change in the shape. Whereas when we were talking about the direct step method, we had to have the same shape of the cross-section upstream and downstream. Standard step approach is a little bit more flexible than that. And it allows us through an iterative process to predict what is going to be the water depth when the channel is changing shape, either going from a trapezoid to a rectangular channel like this is, or it may be that just the channel is getting wider or narrower. So where we were last time is we were looking at this example, and golly, I feel like it just wasn't as clear as I would have liked to it have been. I will point out that there were a couple of things that we added that wasn't originally in the template file that I sent to you. So let me just refresh your memory in case you're revisiting that. Hopefully you saved your file from last time. What we did was we started with that original template file that I provided, and we added in a couple of columns just because it would make our calculations easier a little bit later on. So section 1 is where we know the depth. And this is the downstream section. And we know that because look at the invert elevation. Section 1 is where the bottom of the channel is 5 feet above the datum, whereas section 2, the bottom of the channel is 7 feet above the datum. So that's got to be upstream because water flows downhill. So we know the depth at section 1, and so for every row and every iteration we're going to do, nothing changes because it's going to be the same known depth and the same amount of energy, the same slope of the energy grade line. Nothing changes at this known section. But it's at section 2 where we're trying to figure out what is the flow depth that we're going to try and apply this magic of finding iteratively, starting with a guess, what is an updated water depth, and then trying to improve on our subsequent guesses through an iterative process. Okay, now I've cleared out some of these. I think maybe I had calculated these ones, but I'm going to start with the observed head loss. And by the way, if you're just completely confused on this example, we've got another one we're also going to look through today. And so, starting from scratch with example 2. We won't start with from scratch on example 1. But, all right, so remember that the observed head loss is simply the difference in the energy between the two sections. So E2 minus E1. So E2 was the water surface depth plus the velocity head. And remember, water surface, we're defining water surface as the elevation above the datum and the flow depth. Okay, so head loss is going to be E2 minus E1. And I know I'm zoomed out kind of far here, and that's making the text smaller. I guess I could zoom in a little bit more. But I don't want to zoom in too much more because then I'm panning back and forth and it's less clear what I'm clicking on. All right, so S sub F bar is saying let's identify what's the slope of the energy grade line at the midpoint between section 1 and section 2. So previously we had used Manning's equation to determine what is the slope of the energy grade line at 1 and at 2. And so at the midpoint it's going to be the sum of the energy grade line at 1 and the energy grade line at 2 divided by 2. Okay, so we have the average slope of the energy grade line, and the whole idea here is we're trying to predict how the water depth is changing between 2 points. And so it's this slope that we're going to base that guess of the upstream water depth on. We already have a guess, but we're going to look at what's the depth a different way and then average between our initial guess and the updated depth. Okay, and the first part of that is this calculated head loss. And so here the calculated head loss relies on the slope of the energy grade line at the midpoint multiplied by the section length, which is the distance between section 1 and section 2. So it's the S sub F bar multiplied by the length. Here it's 1,000 feet between sections, and I'm anchoring the reference there, plus the C value, in this case 0.3, and I'm anchoring that reference as well, multiplied by the absolute value of the velocity head at 2 minus the velocity head at 1. So here's the velocity head at 2 minus the velocity head at 1. All right. The calculated water surface is going to be the water surface at 1 plus the velocity head at 1 plus this calculated head loss that we've just determined minus the velocity head at 2. Okay, so 19.13. When we were doing this example on Wednesday, I think I had accidentally referred to the V instead of the velocity head. I was getting some number around 24, and I was a little bit confused. Luckily, we ran out of time, so I was saved by the bell on that one. But later on, I figured out what the issue was. In my formula, see how this reference is going to the velocity head at 1. I accidentally had my equation referring to V1, and it's not V1, it's the velocity head at 1 in this equation. All right. So we've got this calculated water surface, and now the updated water surface is the previously determined water surface, meaning this one, and the calculated one that we've just determined divided by 2. So it's kind of like we're averaging. We're splitting the difference between our old guess and our new guess. So the updated is our old guess for the water surface elevation, our new guess for the water surface elevation divided by 2. So we're finding the midpoint between those two guesses, and we're saying with this we're going to start our next iteration by this is going to provide the depth of the water. In other words, the definition of water surface is the Z and the Y. And so if we're saying this is the water surface at 2, and we know that Z is 7, then we will determine Y, just rearranging the equation. Water surface minus Z equals Y. one other thing, I will scroll to the side here. We have an indicator of convergence with this percent difference. And we've done this before in previous iterative approaches where we're just looking at our input guess and our output guess. And the way we know that we have converged and don't need to do further iterations is when our percent difference is down below 1%. So for the percent difference, I'm going to follow the same approach as we've done in other iterative methods where we're saying it is the updated minus our previous guess divided by the updated times 100. So it's the difference divided by the newer value, which is more correct, times 100. So it's 22.5% difference. And we're just going to look for that to eventually get down to 0, meaning that we're not seeing any more changes in the guess depth. Okay, now we need to come up with a better guess. And instead of just typing in some number at random, 5.1 was my previous guess, I'm not just going to say like 5.2. No, instead what I'm going to say is I'm going to let it be this updated value minus the Z2. And so Z2 is 7 feet. If I anchor that reference with the F4, then I can always refer up to that cell in future rows when I drag my formulas down. So you can see it's saying let's go with a depth of 8.62 because the delta Z is 7 feet. And in our previous guess, we said, we went through this comparison of head loss methods. The head loss calculated with Manning's equation and the slope of the energy grade line, and the head loss that's just based on the depths that I've guessed, upstream and downstream. And we want these two head losses to be the same. So as long as they're different, that means that we don't have a good guess yet, as long as the two head losses are different. So with this new assumed depth at 2, you'll notice I can drag this down, the formula from before, and so now water surface is simply going to be the new depth plus the Z. And area is based off of the shape. This is a rectangular channel, and so area is based on this new water depth. And the velocity is just Q divided by A. So we have an updated velocity head. Wetted perimeter is another geometric parameter that will update based on our new flow depth, as well as hydraulic radius. Actually, everything can be dragged down, so no sense doing it one at a time. I can drag all of this down, and we're getting a lot closer. The difference between the observed and the calculated head loss, the difference isn't as substantial as it was. You also notice our initial guess water surface and our updated water surface are already pretty close, 15.6 versus 15.2. So we're going to see a dramatic reduction in the percent difference term. We're already getting pretty close to convergence. But I can select all of these and drag down through as many iterations as I want. I don't need to go that many because it gets down below 1% after the third iteration. But we can balance things a little bit more, and you can see in the end it converges to a depth of 8.05 feet. And so that is the known depth. And the way we know we've converged is the head losses are the same, and there's no longer any changes in the water surface depth. And so from one iteration to the next, the depth is staying the same. So this is the standard step method. And on Wednesday's class, I mentioned that this is the machinery that's running in the background of HECGRASS. And we've just done this for a single segment, working from section 1 up towards section 2. What HECGRASS does is you may divide a channel up into hundreds or even thousands of different cross sections. And so it will go through and do row by row iterations for each segment of the channel, and there could be thousands of segments. And so a HECGRASS model could take a little while for it to eventually converge, but it's a really powerful approach of breaking up a channel that's gradually getting wider and narrower and the slopes are changing, anytime there's an adjustment in the channel, you just chop it up into lots of little slices. And the more slices you've got, the more accurate your model is going to be, because remember, what we're doing is we're approximating a curve with a line. That same kind of idea of trying to, I illustrated it in a previous slide when we were looking at here, this one, where I kind of gave you the notion that here we have a curved water surface, and when you break it up into sections, what you're effectively doing is you're saying, let's assume that between these points it's a straight line, even though it couldn't just be a series of straight lines because it's a curve. But where there's less error if we break it up into segments than there would be just going with one big jump between the 2 points. So it's a similar idea in this example, where we're assuming that it's a linear change in the water depth between these 2 sections, but hopefully the sections are small enough and close enough together that we're not introducing too much error. Any questions from this example? Okay, as I promised, there's another one, just so we can get a little more practice with this method. In example 2, we are working with the following geometry. Downstream at section 1, we have a known depth, and section 2 is where we don't know the depth. And you can see that what's happening here is it's a circular section, so this is a half circle at section 1, and we're going to say that the elevation datum is 0. So that just means that the channel bottom is touching the datum at location 1. And then here, the bottom of this triangle at section 2 is ½ a meter above the invert of section 1's channel. So this is gradually, if you can think about, it's a circle that's opening up and flattening, the edges are flattening out as it transitions into a triangle in the upstream direction. So if the water's flowing downhill, then actually what's happening is the water is going, like from the point of view of the water itself, the water was in a triangular section, and then it's going to find itself in a half circle when it gets this downstream section that's 100 meters further down. So the other given data that we have is the Manning's N, which we could use to determine the normal depth, and also we're going to use this Manning's N to calculate the slope of the energy grade line at both the upstream and the downstream section. We've got the flow rate, the C value, which is related to the energy loss that occurs when there's a change in channel dimensions. And we're given the normal depth, the critical depth, and then we know the depth at section 1. So let me ask you this. What kind of a profile do we have? How would you classify the water surface profile? Is it mild? Is it steep? Is it adverse? Is it horizontal? Is it critical? Remember A, C, S, M. What else is there? I think that's all. So how about this? Do we have a mild slope or a steep slope? Do you remember the decision criteria for classifying whether the flow conditions are mild or steep? Caleb says mild. You're right. And how do you know that it's a mild slope here, Caleb? It was a 50-50 guess. That's all right. If the normal depth is more than the critical depth, that's mild. So in other words, this is a channel that would support subcritical flow. That's a mild slope. And a steep slope is one that has supercritical flow. And so anytime the normal depth is less than the critical depth, then that means you're going to have supercritical flow and it's a steep slope. here, because normal is greater than critical, that means it's a mild slope. And then since the given depth, 1.5, is greater than either of those, that puts it into zone 1. So it's an M1 profile. All right, so let's go through the process of finding out what is the water depth if we've got this triangular section upstream. Now, just a couple of refreshers. Remember that the area of a triangle is 1/2 base times height, right? So when we do the area, it's going to be y times 2y times 1/2, because that's the area of a triangle. And then when we do the wetted perimeter, we're going to need to know what's this distance on the sides. And so wetted perimeter, like this, is going to be, we're going to use a squared plus b squared equals c squared. So this section length would be the square root of y squared plus y squared. And there's the section on the left and the section on the right to get the wetted perimeter. So we'll get into that in just a moment, but while we're here looking at the geometry, I wanted to point that out. All right, so if you have that template file that I provided on Wednesday, open it and go to Example 2 tab. And like we did before, I'd like to suggest that we add 4 columns to make our calculations a little easier. And I promise next semester I'll fix this template file. I'll add those columns so that the group that comes next time doesn't have to manually insert those. But just up at the top, right click and insert, so that we're going to have the depth y1, and then right next to it we're going to have a column where we calculate the water surface at 1, and then also insert a column next to the velocity, and we're going to separately calculate the velocity head, because we're going to need that for the calculated head loss. And then here in the upstream section next to the depth, add a column for the water surface, and next to the velocity, add a column for the velocity head. All right, so the known section is where it's the half circle. Let's put in the other given parameters. What did it say for our flow rate here? So it's 1.5 cubic meters per second, n is 0.045, length 100. Let's see if we remember that. The 1.5 cubic meters per second, this time we're working in traditional units. The last one was no, this time is SI. Last time we were in traditional. N value 0.045. Z1 we said was 0 because the invert of the downstream channel is at the datum. And then the invert of the upstream channel is at an elevation of 0.5 meters. Our expansion / contraction coefficient is 0.2. And then these two sections are 100 meters apart. Okay, so the given flow depth in this problem, it said that the flow depth is 1.5 meters. So it's 1.5 meters, and water surface by definition is the elevation, the delta Z elevation plus the flow depth. Our delta Z is 0, so it's just the flow depth. Okay, area of a half circle. So 1.5 is the radius of this circle, right? If that's the depth, you notice it's from the center of the half circle down to the edge, so R is 1.5. I usually think about areas in terms of diameter, not radius. Let's see if it's pi r squared. But that would be for a full circle, pi r squared. Am I in the wrong cell? No, yeah, that was in the cell for area. Okay, pi r squared divided by 2. Okay, so that's the area of a half circle where the radius is 1.5 meters. If that's our area and we already knew the flow rate was 1.5, then V is Q divided by the area, and velocity is, velocity head is velocity squared divided by 2 times G, 9.81. All right, pretty low velocity head. Wetted perimeter. Now this is the one where we're going to have the perimeter of a circle is 2 pi r. So the perimeter of a half circle is just going to be pi r. So pi times the depth, which is our radius. Okay, so we've got the wetted perimeter. Hydraulic radius is area divided by the wetted perimeter. And the energy is the Z, the depth, and the velocity head. So here is our formula for the energy. So it is Z plus the flow depth plus, here's our velocity head, 1.509 meters. And now we're going to use the rearranged Manning's equation to tell us what's the slope of the energy grade line just at this section 1. So it's at a point. N times Q divided by the area times the hydraulic radius to the power of 2/3, which is 0.66667. And then all of that is to the power of 2. Okay, now what should the depth be at location 2? Well, think of this as an M1 profile, right? What happens in an M1 profile? It's getting deeper in the direction of flow. So what that means is the depth at 1 is going to be more than the depth upstream at 2 in an M1 profile. So we shouldn't be any more than 1.5. But just to demonstrate that this is a pretty robust like numerical process, it'll converge quickly even if we have kind of a mediocre guess. Let's just say 1.5. Let's set it to the same depth that we experienced at 1. And let's see if it'll converge beyond that. So the water surface definition here, it's the delta Z plus the Y. Okay, so the water surface is Y plus the Z2 that doesn't seem right. Not times, plus. Yeah, something seemed off about that. We're adding. Okay. Yes, so 0.5 meter of elevation and 1.5 meters of flow depth means that our water surface at location 2 is, on a guess basis, 2 meters. All right, so this is our triangular shape, and so the area of that is 1/2 base times height. So the area is 0.5 times the base, which is 2y, times y. Okay, so that's the area of this triangular shape when it's this particular depth. Velocity is the known flow rate divided by the area. so 0.667. And then the velocity head is v squared divided by 2 times g, which is 9.81 here in our SI units. Okay, wetted perimeter. Remember, this is the one where this is the hypotenuse of a triangle that is y on each side. So it's going to be, this length is the square root of y squared plus y squared. And then there's two of them. There's one on the left and one on the right. So the overall wetted perimeter here is 2, because there's a left and a right, times 2 times y squared. And then we have to take that to the 1/2 power. .243. So a squared plus b squared equals c squared. So then to get c, which is the hypotenuse of the triangle, we add together each of the other sides squared and take the square root of it, and then multiply it by 2 because there's the left and the right. Okay, hydraulic radius is area divided by wetted perimeter. And the energy at 2, we're talking about what's the z plus the flow depth and the velocity head. All of those at location 2. So it's the z2 plus the flow depth plus the velocity head. And that gives us 2.023. Slope of the energy grade line, we're using Manning's equation, this Manning's equation. So it's the n value times the flow rate divided by the area times the hydraulic radius to the power of 0.6667. And then all of that is squared. Okay, so the slope of the energy grade line should be 0.0021. Observed head loss is based on the difference in energy at 2 versus 1. So E2 minus E1. And why is there more energy at 2? Mostly it's because of the added elevation at 2. S of F bar is simply the average of the downstream and the upstream energy grade line slope. So we add them together and divide by 2. And the calculated head loss is where we're going to use this formula. It's getting kind of crowded. Let me move this other stuff out of the way. Okay. Calculated head loss. So it's the slope of the energy grade line at the midpoint multiplied by the segment length between the upstream and the downstream section plus the transition coefficient, C, anchor the reference, times the absolute value of the difference in the velocity heads. And so V2 minus V1. I'm making sure to do the velocity heads, not the velocities. Made that mistake last time. Okay, so the calculated head loss, 0.134. And then the calculated water surface, here is this formula. Calculated water surface is our previous guess of the water surface from here, plus the velocity head. Oh, I'm sorry, that was the wrong water surface. I just selected water surface 2. You can see clearly from the formula it says water surface 1. Okay, so water surface 1 plus velocity head 1 plus the calculated head loss that we've just determined, and then subtract out the velocity head at 2. So we have a calculated water surface, and now the updated, we use the old one and the new one and split the difference. So it is calculated water surface plus our previous guess of the water surface divided by 2. So 1.81 is the midpoint between our earlier guess of 2 and our updated guess of the calculated water surface, which is 1.62. Now you remember that our new guess of the depth is going to be based on, it's this minus the delta z. So this is the previous value minus the delta z at 2. Anchor that reference up into the constants. I need to drag all of these known values down through the rest of our iterations and make sure, sometimes you know how Excel has a mind of its own. It's thinking I want to increase the depth by 1 for each row. So no, it should stay 1.5 at each of these. Don't let it think for you. Not this time. There's still an error someplace. Look at how that's changing. What's going on? Did I not anchor a reference? Yeah, it's the reference to the flow rate needs to be anchored. So let me do that. Hopefully you didn't make the same mistake as me when you were calculating the slope of the energy grade line at 1. It needs to be anchored to that reference. And so if I drag that down through all of them, now things look constant with each iteration. Okay, so this is our newer guess of the depth at 2. And with all of the rest of these, I can just drag it down. And I guess I never had my convergence indicator calculated, this percent difference. So the percent difference is just going to be my initial guess of the water surface minus the updated guess divided by the updated times 100. So it's a 10% change in the first iteration, then it gets down to a 9% change in the next iteration. And we can, now that it's all set up correctly, drag all of those down. Oh, we have a problem. It's probably like before where something wasn't anchored the way it ought to have been. Let me see. The area looks good. The velocity looks okay. Wetted perimeter looks fine. Hydraulic radius, energy, head loss is good. It's the calculated. Let's see. Okay. Both the purple and the red are anchored, so it's not that. If anybody sees the issue, I'd be delighted to have you tell me. Sometimes when you're standing in the forest, you can't see the trees. The S sub F. Oh yeah, look at that. Yeah, it's definitely the S sub F. So it must be that I didn't anchor something there. Ah, here we are. It's the flow rate. Again, not anchoring the flow rate. Thank you, Jacob. So yeah. Probably what you had, if you anchored that, then for the second iteration and all the ones after that, that's more like it. How's this look to compared to the one you've got, Jacob? Did you get that the depth converges to 1.26 meters? Good. And if we look at it from a percentage basis, it goes from 10% error down to 2, less than 1, and essentially no changes. You know, it's reached convergence really quickly. So there you have it. That's hydraulic engineering. It's 1:43. We don't really have too much more time. Before we wrap up for today, I just wanted to say thank you for your attention and engagement through the semester. I mean, this has just been, this last year, kind of an uninterrupted nightmare in so many different ways. You know, besides going places in a mask and having to put on smelly hand sanitizer several times per day, just what you're doing right now, getting an education, was disproportionately affected by the pandemic. Having to completely change the way that you learn has been an imposition on your educational experience that I can just only imagine how that must have felt. I mean, it was frustrating enough to teach remotely, but I could imagine it was even worse to try and learn remotely. So I wanted to say thank you for sticking with it, and if you're here today and you made it through the entire academic year, I think it's going to be a lot better in the fall. You know, we're going to have smooth sailing ahead, and so thanks for all that you've put into the course. I haven't yet finished grading the projects yet. I had hoped that I'd be able to do that by today, but it'll definitely be in the coming days. Over the weekend, I'll have a chance to review those, and so your average is available now in Blackboard, and so if you have any questions about that or related to the homework assignment or as you prepare for the exam, please just let me know and I'd be glad to help you out. All right, take care everybody.